In this video, we're going to analyze two-dimensional motion, which is also known as a projectile motion. Balls flying through the air, long jumpers, and cars doing stunt jumps are all examples of the two-dimensional motion that we call projectile motion. Projectile motion is an extension in two dimensions of the free fall motion we studied earlier. A projectile is an object that moves in two dimensions under the influence of gravity and nothing else. Although the real objects are also influenced by air resistance, the effect of the air resistance is small for reasonably dense objects moving at the modest speeds. So we can ignore, when analyzing projectile motion, we can ignore the air resistance. As long as we can neglect air resistance, any projectile will follow the same type of path. Because the form of the motion will always be the same, the strategies we develop to solve one projectile problem can be applied to others as well. Now, let's imagine a kind of equipment that shoots two balls. One is being dropped vertically down, another one is shot horizontally. And let's suppose that both of these balls are shot at the same time. So how the red ball will just go down, we already know it's a simple free fall. And how the yellow one will go down, it's like a very parabolic. The vertical motion of the two balls are identical and they hit the floor simultaneously. Neither ball has any initial motion in the vertical direction, and both fall distance height, h for example, let's just call it the distance h here, and they fall that distance at the same amount of the time. The two balls hit the floor at the same time. This means that the vertical motion of the yellow ball, the one that was launched horizontally, is not affected by the fact that the ball is moving also horizontally. The vertical motion of each ball is a free fall, which is the same for all objects. A careful look at the horizontal motion of the yellow ball shows that it is uniform motion. And the horizontal motion continues as if the ball were not falling. So, if you were to look from bird's eye view, like from the top, from high above the sky, this h distance will be so small that for you or for the bird, the yellow ball will be just similar to a ball going on a horizontal line on a surface. If you were to look from the side, let me draw the side, for yellow ball and a red ball, both of them are free falling. And the bird, looking from the above, will see that the yellow ball is just moving horizontally from initial position to the final position. And the red ball for the bird will be just in its place, not moving horizontally. In fact, there is a device that you can actually do this experiment and analyze the motion, and you will see that these motions, the free fall for yellow and the red one, are exactly the same, and the horizontal is a uniform. So I'm gonna write in summary: horizontal motion is actually uniform for the yellow ball, which means uniform means that the velocity is not changing. Is not changing, which means acceleration horizontal, I'm going to call it x, equals 0. So horizontal motion, in a horizontal motion, for a projectile motion, there is no acceleration. So the vertical motion for the yellow ball is actually a free fall, which means the AY equals negative g. So, and these two combined together, horizontal and vertical motion, for the yellow ball is projectile motion. So these two are together projectile motion. So in any time you are seeing a projectile motion, you can think of a combination of horizontal and vertical motions together. It is very important to mention that initial horizontal velocity has no influence over the vertical motion, and vice versa. Initial vertical velocity has no influence on a horizontal motion. So we would find something similar if we looked in a detail at any projectile motion, so we can state a general rule. So the horizontal and vertical components of an object undergoing projectile motion are independent of each other. So I'm going to write that for you. So vector components can be used to analyze projectile motion by simply breaking up the motion into x and y components and treating them separately. Well, it is instructive to first analyze the motion of an object projected horizontally or parallel to the level of the surface, and then vertically. And when we analyze horizontal and vertical motions separately, well, kinematics is a very useful tool for us, so we can use kinematics equations to analyze this. For that, we want to make a little bit notations so we will be clear or summarize in a notation form what are the kinematics equation for x and y components. Well, let's make a chart. So I'm going to write on the left side x component of the motion, and then y component on the motion on the right side. And then I have, let's put variable in the middle, variable. So what do we have? We have a displacement. We have acceleration. Final velocity, initial velocity, and elapsed time. So we have for the x component displacement, I'm gonna have as x. In some cases we call it delta x, or let's just put it delta x where the x initial is involved, and delta y on a y component. And then we have a ax for the x component, ay for the y component. For the final velocity, we will have a vx and vy. For the initial velocity, we will have v naught x, v naught y. And for the time is the same for both of them. So it's important to know as well, because it takes the same time for the object to fall and then go to the horizontal motion. Now the equations, for our first equation, we can write Vx equals V naught x plus AXT. For the y component, we will write Vy equals V naught y plus AYT. Second equation, we can write delta x equals 1/2 V naught x plus Vx t, and then delta y equals 1/2 V naught y plus Vyt. For the third equation, we will have delta x equals V naught x t plus 1/2 AXT squared. And for the y component, we will have dy equals delta y equals V naught yt plus 1/2 AY t squared. Finally, for the fourth equation, we have a Vx squared equals V naught x squared plus 2ax delta x. And then same thing for the y component, Vy equals V naught y, Vy squared equals V naught y squared plus 2ay delta y. Be careful and remember that the time for both x and y components are the same. So to better picture the situation, I will follow up with examples in a separate video. So stay tuned, and thank you for watching.